All right, everybody, welcome back. So I want to use this video to kind of go over a couple of things that might be convenient for you as you're getting started doing your, as you get started actually kind of assembling your board. There's a couple of things that aren't really into the routing and stuff, but they're things that are going to help as you're putting parts down. So one of the things that's going to really help is quite often you'll find parts through DigiKey, through Mauser, through Newark. A lot of those places now have links to 3D models, links to footprints, links to parts. The reason for that is a lot of manufacturers have found now that if they include those things, if they include the footprints and the schematic symbols and the 3D models for their parts, people are much more likely to buy them. Because if you're an engineer and you have control over the bill of materials, you won't always. Sometimes you'll work for a company, and if you want to choose a part, it'll go through a big purchasing process where they're going to make sure that you're not being lazy and you're not spending the company's money to be lazy. So a lot of companies, it's going to be if you're going to sell 10 million of something, you're not going to pay an extra 10 cents for something. Just that's $1 million, right? Just to make it easy. But for people who are engineers at smaller companies that do kind of small to medium production, quite often, if it saves the engineer an hour or a half hour, it's worth it if it costs an extra $200 or so for the part. So they know that people are more likely to go with parts that make their life easy. So quite often they make these parts available. So I'm going to first start off by just showing if you want to add a part using a library that you found online, then I'm going to kind of show you how to do it in KiCad. So to start, we'll start looking at this SparkFun schematic here. So the SparkFun schematic. One thing this SparkFun schematic had was a micromod connector. So the micromod connector, this is just an M2 connector, but it's a fairly complicated part. You're not going to want to build this by scratch. It's got like 72 pins or something. It's got a really complicated 3D shape. But the good thing is it is available online. So you can go online to DigiKey. You can find this part. I looked it up. I think it was, do we have it here? Well, maybe not, but I had it at one point in time. Open on DigiKey. You go on DigiKey, is it here? Yeah, right here, okay. So this part's available on DigiKey. You go down here, it says, hey, here's your product drawings. Here's your EDA models, right? So you can find your EDA. EDA is electronic design automation. KiCad is EDA software, right? So the EDA model, you can use Ultra Librarian or SNAP EDA, but if you go to SNAP EDA, what you'll see is you can just go. So now I'm logged in. I have an account. I'm logged in, but you can create an account. It's free. And you can go to download symbol and footprint, and then you can just choose KiCad version 6 or I'm using version 6, so I'd use version 6 or later. It converts it and it creates it for you to download, right? So I downloaded it. So how do you go from that to something in KiCad? So I'm going to show you how I do it. So the first thing is you want to extract it. I've already done this. So you want to take that zipped up file, you want to extract it into a folder. The key thing is you really want to put that folder in with your project. So what you don't want to have is you're using one computer at home and you have all these symbols and stuff, and then and your symbols and your footprints are all separate from your project, so you go somewhere else. So you can either put those symbols and stuff in the appropriate folders in the KiCad software, or you can associate it with your project. So I would unzip, I'm not going to for this example, but I would take that whole unzipped folder and drag it into a folder of your actual project, so that within your project folder, everything is self-encapsulated. KiCad is usually pretty good. KiCad is pretty good about using relative file paths. So if you're selecting a symbol or something, it'll use a relative file path if it's within your project, if it's shown as a project library. So let's say we've downloaded it. Let's go from here. So if we've downloaded it, and we go back to our parts here. So what I have done is I have created already this, we'll skip it. So we have this part, it downloaded the footprint and everything should be downloaded. So let's do this is the one that I created before. Let's do add library. So we're going to add library. We're going to do a project library. It could be global. It doesn't really matter. For right now, it's just temporary. So now this is the download that I had. So this was the downloads M2. So I unzipped that folder to this M2con, and then it's this KiCad symbol library here. So this is included with SNAP EDA. They'll include a symbol library that you can open. So we'll open that up. Oh, it already exists because I already did this to make sure I didn't screw it up. So it already exists, but if it hadn't already existed, it wouldn't be there. So we open it up, and what do we have? This is it. So this is the footprint for the part. Now, this opened in its own library, so usually the first thing I like to do is I will take that, and I will copy that, and I will go into my personal folder that I had for the LoRa demo, and I will do paste symbol. Okay. So now this part is part of my library. So this is part of this is just associated with my library. If I save it, it'll save it with my library. Okay, so there's a couple of things we can do once it's here. So one thing we might want to do is, I don't necessarily like the name, 21992304. That might be a name that means something to SNAP EDA. It doesn't to me. So what I might do is I might just go save as, make sure it's still in my LoRa. Oops, sorry. I might just do save as, and then I'll just call it like M2 or something like that. And then there's probably a better way to do this, but I'm just going to cut the old one, right? So I saved it as under a different name inside my library. There's probably a way to rename it. It's probably just right here, right? If I just do, well, I don't see it anyway. Yeah, but anyway, there's probably a better way to do that. That's the way I do it because I like to just fly by the seat of my pants in everything that I do. So now we have our footprint here, and we might want to clean it up. So this shows a whole bunch of all the pins are set as passive, but this should be all the pins that we have for our thing. And you see what they did is they overlap two visible pins. So we talked last time about overlapping pins, and I said don't do hidden pins. Overlapping hidden pins doesn't do anything. Hidden pin's a hidden pin. A hidden pin, the software will try to, based on the name of the pin, it'll try to connect it with signals. That's not a good idea. In this case, they just did, to have two things that are connected to the same thing, probably the shield will be grounded. They just overlap the two pins so that any wire that's connected here will automatically connect to both pins. That's fine. That's a sloppy way to do it. There's not really a good way to do it. Probably if it were me, I would have just had shield 1, shield 2, and just shown them as two separate pins. They overlapped them. That's fine. Overlapping's fine, but it's just ugly a little bit. So this looks pretty good, right? I mean, this looks pretty good to me. We got a bunch of junk here. We could, if we want to clean this up, we can do that. I don't know what this means. I don't know what any of this means. It's what came with it. But overall, the footprint looks okay. The number is J, so it's a jumper. So we can go with J. That's probably fine. This all looks good at first glance. So let's just save that now. So now that's corrected. So the next thing is to go to the footprint. So the next thing is, oopsies. So the next thing is we go to the footprint. Yeah. So I created a new library called M2Con for the footprint. What we can do is we can add library, project library, and we can go to M2Con. Oops, did I mess it up? Ah, crap, I may have messed it up. Okay, well, let me go back to interesting. Oh, here we go. Sorry, I had to go import footprint. So import footprint from the KiCad.mod. So this is the footprint file. Okay. There we go. Okay, so we imprinted. So we imported the footprint. Where did it import it to? Whoa. Okay, so we're gonna. So this is the footprint. We're just gonna change the name of that to m2.con, and we will save it to our folder. We'll save it to the LoRa demo folder. Okay, there we go. So now we've saved that footprint to the LoRa demo folder. Always check. So when you find a footprint on the internet, always check to make sure it's correct, because quite often it's not correct. And this looks okay. The references here all is okay. Everything looks good. It looked to me when I looked at it like everything was right, but you always want to triple check to make sure it's correct. We're going to do something else. We're going to add a 3D footprint to this. So we're going to go, if we go to the, It's footprint properties here. We go to the footprint properties, there's all these sort of general properties. Oh, that's where we change the name of it, I guess. And then we can go to this 3D model, and if the part that you downloaded came with a 3D model as this did, it's really easy to just add the 3D model to this. So we can add a 3D model here, and it should be a step file. And when we add that step file, it plops it down on here. Now you'll notice it's not plopped down right. So it's all cutting into the board. So the nice thing is, and actually KiCad does a pretty good job of this. So you have this 3D file that shows the footprint, but it's all wonky. It does a pretty good job of letting you sort of view it. So what you can do is you can rotate it to get it right. So that looks like it's rotated right, I think. Now there's one big hole and one little hole, so we're gonna sort of check that to make sure it's right. It looks like it's way off center, right? So it's way shifted down here, so we're gonna have to shift this thing around. So let's shift it. I don't know which way is which. That's not right. There. Yeah, is that, oops. Is that right? That looks right. So just zooming in, looks like the feet are on the pads, so it looks like it had to shift over 2 millimeters. Let's flip it over to make sure, is there a big peg in this hole? Yeah, there's a big peg in that hole. Is there a little peg in the other hole? Yeah, there's a little peg in the other hole. So it looks to me like this is fairly well placed on here. Now the 3D model is only used for visualizing this. So the 3D model is literally only used as so that you can see what your board looks like. There's a reason for that. The benefit of the 3D model being there is it avoids what's called, steric hindrance, or sometimes in chemistry it's called steric hindrance, which is when you can't bond two molecules together because physically the other part of the molecule prevents it from connecting. So like, let's say you have two long molecules that are sticks and you have a binding thing here and a binding thing here and one here and one here. If they can't physically touch those two binding sites together simultaneously, that's called a steric hindrance. Same thing happens in PCBs. Quite often the footprints will fit. You can put the footprints for a part without overlapping, but the three-dimensional body of the part will collide with the three-dimensional body of another part. This is really common with capacitors. So capacitors have small little leads that go into small little closed holes, but they have a big giant can. And quite often that big giant can will bump into things next to it, right? It's like me on a subway, right? When I'm in Japan, my big giant can collides with things around me on the subway. It's a real problem. Anyway, I'm gonna get in can trouble here. So this looks like it's on there. It looks like it's good, and we're gonna click OK. So now that 3D body is associated with this footprint, we can do File, Save. And if we really want to sort of put all the pieces together, we can go back to our symbol, and we can in the oops, where's the symbol properties? What's the preferences? Symbol properties, yeah. So here we can go to the footprint. Oh, it looks like it was already associated with it. Oh, well, we're not going to do that. We're going to, well, it looks like that footprint, there was something listed in the footprint field, but it was not what we want. So we're going to go to our footprint, which we just moved over to our folder, which was here. Nope, that's not it. LoRa demo, M2Con. All right. Oh, so we're going to associate it with our footprint, and then click OK. We're going to save it, and then let's say we added this to our project. Let's say we were really doing the full Altium thing. So let's go back and add this to our project. And we go to, well, let's close that. What do we call it? This was LoRa demo, right? LoRa demo, M2Con, click OK. Place that somewhere, and then just for fun, we're going to annotate, and then we're going to update PCB from schematic. Okay, now look at that. It added our header that we just had here. So it added that header that we just added. And let's see, and we have this, so this is the other stuff we had in there. I'm kind of jumping the gun here. Going here, I was just showing you that it works. If we go to the, sorry, I'm not very fast with, this is like the 5th EDA software that I've learned. So I kind of mix and match different things. If we go to 3D viewer, yeah. So it's green, which means it's having an issue. I don't know why it's green. It's probably a clearance. It's probably a passing through the board clearance kind of a thing. It's probably a weird collision. We can figure it out later. I don't really care, but we. Let's run the design rule checker. Yeah, it doesn't like that. Well, not quite sure what that is. We can figure it out later, but for right now, it doesn't like the 3D body, which is fine, but it's there. So, all right. That's well, no. Let's keep going. Let's keep going. Yeah, we'll save that. It'll be fine. So let's keep going with our part here. So, well, let's first of all get rid of that. I don't actually want the M2 connector. And then let's keep going with what we were trying to get from the Spark Fun. Where's Spark Fun? There we go. Okay. So a couple of things we want to add. So one, let's add, I do want to add an SMA connector. This module has the SMA connector on it, but I'd like to add an SMA connector anyway. As an extra one, like a larger SMA connector, so we can find that in the parts. Let's do the 100K resistors. So they have pull downs on the transmit and receives, and they have pull ups on the reset and chip select. So let's do that. Let's add the but actually, first of all, decoupling. So this is a little weird. So I want to do this. So what's going on here is we had so remember we had this power enable where the power enable was designed to cut off. If this thing is turned off, if this thing is pulled low, it will cut off VCC and 3v3 from 3v3 in and VCC in. So, and this VCC is the high voltage. The VCC is the 5 volts that this radio really is a high-powered radio. It's a 1-watt radio. So the amplifier for that RF signal has to go over 3.3 volts, so it wants a high voltage. It wants like a 5-volt source. So we have to feed it a 5-volt source, but then there's also the 3.3 volts as a communications reference. So the 3.3 volts is used for that. And what they do is they have VCC, which is 5 volts, and they have a jumper, and then they have a 5 volts over here. So this is the same signal that is given 2 different names. And the reason it's given 2 different names is so that it can exist on both sides of this cut trace jumper. And the cut trace jumper allows us, the reason we'd have a cut trace jumper is, let's say we're doing this and something's going wrong. We're drawing too much current. We want to say, okay, how much current's my radio drawing? How much power is my radio actually using? We could cut this jumper with a knife and then connect wires to each side of the jumper, and then we could we could look at it we could hook it up to a multimeter or something to measure the current to see how much current is being consumed. We could hook it up to an oscope, a current measurement probe on an oscope to measure how much power this thing's actually using. But it requires us, if we want to do something like this, where we have a signal which is across a fuse or across a jumper, we have to give that signal 2 different names. So in this case, they're using VCC and 5 volts. I'll probably do the same, but that's not great, right? So VCC and 5 volts. What do we have on the other side? 47 microfarad, 10 microfarad, both electrolytic, a 0.22 and a 0.1. So they're using, we've talked about capacitors. Why you do this, you want different frequency response. A 47 microfarad capacitor, that's a big boy. So 47 microfarad, that's probably because, again, this is a high power radio. When you first turn on that radio and it goes from consuming 0 milliamps to consuming 700 milliamps, that's going to be quite the jump. If you had that source coming from across long jumper cables from a long distance away, you don't want to have a sag in that voltage, so you want to have a good decoupling capacitor right there on that side of it. So let's build that. Let's build this first of all on our system. So our voltages were labeled, so we also labeled them VCC and plus 3V3. So now we're going to create a 5 volts across this jumper. So first of all, let's add symbol, and let's go to recently used. So I think it was. So you're gonna see the thing I do. So right now, all we want is a 2-terminal symbol for this. We can choose the footprint we want later. So we just want something that makes it clear that this is a bridge jumper. So maybe something like this. So we'll do a bridge jumper. This looks like what they had. And again, I just searched for jumper. We have a bridge jumper. There's no associated footprint. Oh, they have some options here if we wanted it. I'm curious. Let's look at the options. It's not bad. Yeah, this might be what we end up going with, but for now, let's just do no footprint. Okay. So we're going to place that jumper here-ish. So on one side of the jumper, we're going to have VCC. We're going to hit escape. For me, I just like to copy paste. That avoids any naming issue. A lot of times if you try to name them, you type it in wrong and it gets the signal wrong. You don't notice it. It screws everything up. So then on the other side of it, we're going to call 5 volts, just like here. So on the other side of this, oopsies, we're going to place add power, and we're going to call it plus 5. So, okay, so see, all right, so this is interesting, right? So what happened is, see how I couldn't, see how I can't connect that to the jumper? What happened is, when I grabbed the jumper, it grabbed the jumper from the center, and the jumper was an odd number of grid spaces wide. So when I grabbed it from the center, it moved the center of this jumper to the grid, but the ends of the jumper were then not on the grid. And when I moved the VCC over, it grabbed it because it snapped to the nearest thing. So I don't like this. I mean, we can just put these close and move it, but here's the fix if you run into something like this. The fix is to get this jumper back on a grid alignment is you do, where's my grid? Well, let's just make this big for now. Where's my, there's a better way to do grid, I just forget. So grid, we'll do 1.27. And then now, so now our grid is half spaced. So now we can be back on the grid. So now if we go back to the grid, we can switch back to our course grid. Okay, and so now that should be, so we set our grid to to slightly more fine, moved it into what will be aligned when it's back to the course, and then we'll do this. Okay. So now we need to add some caps. So we have to have 2 electrolytic caps and 2 ceramic caps that look like. So we're gonna, we can hit the A key if we're trying to be fast here. Add part, we can do. So a lot of times when you try to type something in, it does it a little wonky. So cap polarized small US, I always go for the small and US. So normally the US does everything big. I like the small symbols though, right? So this is gonna be like, what does the US do good that's really small? Mini bike races? Is mini bike races a US thing? I think so. Yeah, mini bike races works. We do mini bike races. Like those clowns that ride the little tiny bicycles, we do that pretty good. I don't think any other countries do that. Maybe they do. Well, let's take credit. Let's take credit. Okay, so we don't care about the footprint for right now. We're just gonna click OK. We'll put that right here. Let's drop a second one. So now I've copy pasted this without an associated footprint, which means I can choose 2 different footprints for these, which I'll probably want to do. Now let's drop 2 normal capacitors. Device capacitors. I'm looking for capacitors small. Let's just do that. Okay, so 1 capacitor small, grab it, Control C, Control V, paste it. Okay. So now when we're saying, okay, we need a big electrolytic, we need a medium electrolytic, we need so 2 different size ceramic caps. Now I'm going to go back to the library. So now I'm going to say, okay, what actual footprints do we have for this? So let's go back to the parts library, the stuff we actually got. And let's look at our capacitors. So it looks like we have this. It looks like we have a 2917. That's a weird footprint. 2917, 100 microfarad tantalum cap. Let's go with that. Who knows? It's what we got. So 100 microfarad tantalum cap. The main thing is this is a 2917 footprint. I don't think we're going to find 2917, but we'll find something close. 2917, maybe we'll find it. Who knows? So it's 100 microfarad. So right now what I'm going to do is I'm going to say, okay, I'm going to change the value of this to 100 microfarad. Changing the value in software does nothing. The only thing changing this value does, it doesn't change anything physically. The only thing changing the value does is it tells you as a designer, you have to, whatever this capacitor number is, you have to pluck out a 100 microfarad cap and solder it into this capacitor position. So now let's find the footprint for this. So I'm looking for, what was it, 2917 or something? I don't know. So it's a, I think it was 2917. 2917, yeah. So we're going to go to the footprint of capacitor tantalum. Probably gonna be, yeah. So do we have 2917? We don't, as I suspected. We don't have 2917. We have 3216. That'll probably work. So these pads are so big that it'll probably work. If we're really trying to be correct, we should create the thing, but 2917, 3216, pretty sure the capacitor is gonna fit just fine. To be safe though, we'll do a hand soldered one. So we look at this hand soldered one. Yeah, so this is 3216. How big is that? Oh yeah, the pads. Okay, yeah. This is actually pretty big. It doesn't necessarily. It's hard to see what size it is here, but this should be 3.2 hundredths of an inch by 1.6 hundredths of an inch. So that's going to be pretty no, that's going to be 0.32 inches by 0.16 inches. This is a pretty big cap. So let's choose that, and then okay. Let's go to the other cap too. So the other cap was supposed to be a 10 microfarad, I believe, and I believe we have a 10 microfarad cap. So if we go to the parts thing, tantalum, 10 microfarads, yeah. What footprint? 1206. That's 1206 footprint. So we're gonna go back here. We're gonna select this one. First thing we're gonna do is we're gonna change the value to 10 microfarads. And for the footprint, we'll go. So we're still in the tantalum caps. There'd better be. Wait, what size is it? What's 1206? Huh? Are these metric? Are these metric? Are these sizes metric? Well, we'll check later. We'll sanity check ourselves later. Interesting. Maybe these sizes are metric. It's very not super clear. So if they're metric, we'd have to triple check our work here, but we can do that in a little bit. So let's just go to the capacitor SMD. Yeah. So it was 1206, right? Okay, I'm losing my mind here. 1206, yeah. So we'll just go to 1206. And solder. Yeah, I'm a little worried that those other ones were the metric sizing. So if they were the metric sizing for the other one, we'll have to do a conversion. But for now, for this one, we'll just pick this. Should be fine. Actually, it might not be fine, because is this going to show us a polarized? Yeah, this doesn't show polarity. So if it's tantalum, it needs to show polarity. Okay, so okay. This will show us a conversion. So 1206 is 3216 metric. Let's go back to tantalum. So let's do 3216. Yeah, I bet the other one was metric. Yep. So let's choose this. Okay. So then if this one was supposed to be, okay. So if this one was 2917 imperial, so this one, so 2917 is going to be, so 17 is going to be a little bit less than 45. I bet it's this. I bet it's this. So let's bust out the old calculator, okay? So 17 times 2.56 is 43. 2.54, sorry. 17, 2.54 is 43.18. And 29, 2.54 is 73.66. Yeah, well, close enough. So I bet it's this one. I bet it's this one right here. We're looking for... Okay. Sounds good. All right, so now you got a real... Sorry for making you wait. You got a real live view of what we deal with. These other two ones were going to be ceramic, and as long as they're reasonable, we should have that in 0603. So 0.22 microfarads, we probably have in 0603. Let's check. So we have we have 0.22 microfarads here. No, that's not 0.22 microfarads. 0.22 microfarads. Now check the voltage rating, right? This one goes up to 25 volts, and this is for a 5-volt supply, so that's okay. When you'll notice when you get up into these bigger ceramic caps, yeah, we have an 0603 10 microfarad capacitor, but that only is rated to 6.3 volts. I probably would not use a 6.3 volt ceramic cap if I had a 5-volt source, because again, if that voltage even temporarily goes over 6.3 volts, like even a little transient spike, you can fry that cap. So I'd probably want to go with a 16 or higher voltage if I was expecting 5, just to be safe. In this case, the 0.22 that we have is fine. That's 0603. So we're just going to go back to the capacitor and just pick 0603 footprints for both of those other ones. So we're going to go back here. And for this one, we're going to pick 0603 and solder. And the value here was going to be 0.22 microfarads. And this one was, I believe, was it 100 nano? So this one was, yeah, 100 nanofarads. Yeah. So for this one, and 0603. Okay. Now I'll show you in another video how to use if you want to throw down all of your symbols and then you want to add the footprints at the end right before you move them over to the board, I'll show you how to do that later. And then we have to add this one. We have to add the footprint for this cut trace here, and I believe this jumper. Yeah. So this is if you look at the jumper footprints, you find all these different types of bridge footprints. You can kind of pick what you want, right? So it's got to be a closed one. They got it's got to be a 2-pin closed one. They got some cool ones here. That one looks fine, so we'll go with this one. Now, I'm going to probably call it quits here. It's been a long enough video. We did the importing symbols and stuff, which is an important one. Let's annotate this and just take a peek at these parts. Update PCB from schematic. Now, you'll notice something that didn't change. This M2 connector did not go away. So this is one of the problems with KiCad is a lot of times if you delete something in the schematic, it doesn't necessarily delete it in the board. And this is the basic functionality of having a tool that compares, hey, does everything that exists on the schematic exist on the board, and does nothing that doesn't exist on the schematic exist on the board? That's missing from KiCad. So in this case, we have to manually delete this. But yeah, it did look like we have that cut trace, we have that big old capacitor. If it were me, I would probably, click here, and then if you see, as we click, we can see our grid size. So look at the bottom right corner of the screen. If I click here on this pad, if I click about here-ish, and then I move over here, my delta X is like, oops. Yeah. So sorry, if I start here, my delta X is like 119. Here it's like 126. So we can kind of get a rough 119 to 126. We can see it's about 7 millimeters across. I could sanity check myself and just go, hey, let me look up the data sheet for this capacitor. Is the body of it about 7 millimeters? This is really important to kind of constantly be sanity checking yourself and saying, hey, is this reasonable or is this unreasonable? A lot of students are way off. They do something and they, even just a quick little, hey, does that seem about the right size? They don't do it. So a lot of students all the resistors they'll have will be something crazy. Instead of 0604 imperial, there'll be 0604 metric. It can be hard to see the difference when you're actually actively working. You might just say, oh, that's the size the chip is, that's the size the capacitors are. So we're kind of sanity checking ourselves doing this. So, all right, everybody, I'm gonna call it good there. I'm gonna cut it, and hope you enjoyed the video.